Hi, good morning, ladies and gentlemen, distinguished guests. Thank you for coming out to the NEESat Asteria Subsystems presentation. My name is Jesse Viera, and I'm joined here by my teammates, Mr. Anthony Fernandez and Mrs. Kristen Kim. We're led under the advisement of Dr. Pradeep Shinde and Dr. Tosunoglu, both members of the FIU Mechanical Engineering Club. So a little bit about this project. A few years ago, the Near Earth Explorer Club began participating in what's known as the NASA FunSat competition. This is a competition at the university level to with hopes of motivating and sparking an interest in the CubeSat development. Some of the subsystems that will be stepping in to help for this second phase of the competition will be the internal cooling system, the optical structure, and the attitude and orbital control system.
So just a brief overview, the intent of our satellite is to record data pertaining to the weather and then transmitting that data back to a ground station here on Earth to then be readily made available to the public. We will be developing an internal thermal cooling system that will dissipate all the heat generated by all the internal subsystems. Our optical origami system will be able to expand and contract and will therefore minimize the payload, minimize space occupancy, as well as increasing any optical performance that can be done in the future. The orbital trajectory and attitude control system will maintain the altitude of the satellite for its entire lifespan. The team is currently leveraging previous design work and also the following sources listed behind me.
So to give a quick run through our standards, California Polytech State University developed the CubeSat Pico satellite standards that will be used for the competition-based portion of the standards, as well as the FAA standards for our weather balloon testing that will take place hopefully in the end of the summer, as well as ASHRAE standards for our thermal cooling system and the multiple NASA technical standards that were used as seen above. So some project parameters limitations. We're currently limited to a 10 by 10 by 30 cubic centimeter space limitation, as well as a 4 kilogram payload capacity. Currently we'll be experiencing 93-minute periods of our orbits, which will equate to about 16 orbits per day. 7 of these orbits will be used for collection of data. 5 of these orbits will be used for data transmission back to its ground station on Earth, and the remaining 4 will be used for housekeeping, which includes sensor checks and attitude and orbital adjustments. So some limitations for each of our systems. Our interior cooling is limited to our conduction and radiation heat transfer, and also our 0 to 40 degrees Celsius operating temperature of the internal components. Our optic structure is limited to the configuration of the internal components because of the need to expand and contract the optic system. And our attitude and orbital trajectory system is limited to its 20-year mission life. So to begin with our internal thermal cooling system, our calculations are currently being developed in 2 phases. So phase 1 will consist of conduction heat transfer through the components through the hot phase of its orbit and the cold phase of its orbit. And we will be developing in the summer the radiation phase, which will also include the hot and cold phases of orbit. So as you can see on the bottom left, we have our energy balance equation, which is pretty much just assumed to be the heat output of each internal component, or the internal component system. So we have our optic system, attitude control, communication, and then our microcontrollers, which will be used to control sensors and program. Currently, we're assuming 100% power input as heat output to be able to assume a worst case scenario so that we make sure that we're designing effectively. And we are currently experiencing about a 40-watt heat output that needs to be managed. So as seen above, we have one of the many components that are seen in our system. This simulation was performed by a previous team, and their research and information that they gathered is being used, or we're using it on our team to further optimize our system and manage the temperature variations better. So to be able to manage these temperatures, we're going to be using what's known as a phase change material, specifically a solid liquid phase change material. So a phase change material is any material with a sharp enough melting point and a large enough heat of fusion to be able to, and it stores its energy in its chemical bonds, and the energy is released back into the system when it changes phase. So when it experiences a phase from solid to liquid, or vice versa, back from liquid to solid, it releases large amounts of energy. So we're considering PCMs around 45 degrees Celsius because we believe that's optimal for our system, and it will be able to maintain our components between our 0 to 40 degree service life. And we're currently looking into inorganic technical grade salt hydrates and organic paraffin waxes. But as you can see below, we are mostly looking into organic paraffin waxes because of their cheap cost and availability, as well as economic feasibility. So with these phase change materials, we're going to be developing a heat exchanger. We currently have two options. As seen above, our first option is a PCM design where it's per component. So we have probably about like 15 to 20 little mini like heat exchangers directly attached to each component. Our second is a central phase change heat exchanger, which is connected by heat pipes to each component. We are currently pursuing the second option because it's going to be easier to mount to the structure of the system, easier to perform vibration analysis as well as other stress simulations. And it will also minimize the error when, as like it could happen with the material leaving the encasement. So we want to make sure that all our material stays inside.
For the design of the origami optic system, we are developing our design based off of previous work that has the following parameters. It currently has a weight of around 0.56 kilograms, which is well below the weight constraint. The optics tube length is fixed, and it has a length of 250 millimeters with a diameter of 25.4 millimeters, and the diameter of the lens itself is 25 millimeters. So we want to go ahead and reduce the weight by about 30%, reduce the length by 90%, so that way it has a compressed length of about an inch. And the cost right now is looking at $450, and we want to reduce that by 30% as well. For the design, we know that one end is going to be mounted onto the satellite, and the other end will contain all of the optical components. We wanted to focus on three main design points, and they're the shape, the fold, and the method of the expansion and contraction. For the shape, we wanted to play with the idea of having a rectangular prism, a hexagonal shape to accommodate any folding, but we ultimately decided to go with a cylindrical shape simply because any other shape would distort the image for the optic system. For the fold, we decided to look at three different options, and they are a complex helical fold, as seen to my right, the first image, a Miura fold, which has a reputation of having structural integrity, and it's seen in this image right here. It's a series of parallelograms and tessellation. And our third option is using a pleated design, and this is the one that is most desired simply because it will suit the cylindrical shape. For the method of expansion and contraction, our three options are using a motor and a track that will physically expand the structure. We also have the option of using an internal helical structure, which is not really desirable because we feel like it'll be almost impossible due to our size constraint. And our third option is using a thermoplastic material that will be able to expand under a certain temperature. And we're also playing with the idea of combining the internal thermal cooling system with the origami optic system, so we may direct the dissipation of the heat to the optic system to expand it.
Right. So systems in orbit at this altitude will experience an orbital decay. This is going to be due to the atmospheric drag that it experiences. For this reason, it's important to employ an attitude and control system to maintain that trajectory for the given mission lifespan. For the development of our attitude and control system, this will occur in two phases. Phase one will be a lifetime analysis. Phase two will be pinpointing a thruster that we'll use for the attitude and control system, designing, manufacturing, and testing it here at FIU. Above you can see a figure of our predicted orbital trajectory, which we used using MATLAB code that we developed. So as noted, our mission lifespan will be 20 years. We conducted our analysis using MATLAB, and our program predicted that our unassisted satellite will be in orbit for 9.9 years. From here, we leveraged a similar program by the Australian Bureau of Meteorology, and ran their program and got a lifespan of 8.5 years. From here, our team feels confident that we can use this data to calculate the force needed to accomplish that 20-year mission lifespan. So it was important when choosing our thruster that it was both lightweight and fit with our constraints, our limited constraints. For that reason, we went with a micropulse plasma thruster. We believe the capabilities of this thruster are well aligned with the needs of our system. And also another important aspect of it was that it produces a low level of thrust. The adjustments that we will need to make, that we predict we'll need to make, will be very sensitive, so it's important that the thrust doesn't overwhelm the system and throw it out of its trajectory. For our future work, this month and throughout the next summer and fall, we will be finalizing our designs and conducting our simulations, as well as a cost analysis and finalizing all materials for our designs. We'll be leveraging both the plasma forming lab and the AMRI lab here at FIU to conduct our stress analysis, vibration analysis, and the thrust we're generating from our thruster. Elements of global design. For the global aspect, One of the driving forces behind the motivation of the CubeSat industry is it's becoming a more cost-effective way of sending monitoring satellites into orbit. Another global perspective that we're taking into account is we will be collecting climate and weather data and making this readily available. And lastly, in an economic perspective, environmental aspect, we're taking into account is not becoming a part of space debris and complying with our standards. That means upon re-entry, we'll ensure that it's retired properly and that our system is vaporized upon entering the atmosphere.
Pictured above is our Gantt chart. We will begin finalizing design options with material selection and a cost analysis throughout the summer, and in the fall we will hope to manufacture and assemble and also further our analysis and testing.
Any questions?
I have a question about your optics. So you expand, is this going to be like my telephoto lens, or is this an expansion of the lens?
It's going to be an expansion of the tube, so that we just want to have the optic system at a shorter length upon launching, and just to reduce the payload and all that stuff. So it won't change the optic system itself, it's just the tube, the physical structure of the tube.
And why would you want to do that?
It will enable for future design to have a better optic system to have zoom capabilities, but for now it would just be to have a compressed system.
Yeah, and expand upon.
And expand when
once
needed.
it's nested into its orbit.
Also, in other words, like it will save your space before launching. So after launching, it's gonna expand, so you can have this extended to. I think that's what you mean.
Right. So to add or to conclude what he said, pretty much we could have a better optic system, which will require a longer length and still be in range of our parameters, our 10 by 10 by 30. And then when we launch and are in space, we could extend past those parameters
To have a better optic system.
to have more definition in our photos and all that.
Now, are you going to research the lens, the bend, the use, how the lens is made? What, you know, I'm thinking about the Hubble, where their mirror was off a few 10,000ths of an inch, and it warped the picture.
Right. Well, like we said, we're working off of previous work, so that work is already done already. So my structure should not hinder. It's not supposed to hinder the optic system or the image at all, which is why we chose not to change the shape, because that would definitely distort the image. So that work has already been done already. So
you just figured out the tube and how
yeah,
you
and to compress it and reduce the weight and reduce costs, and at the launch we have more space inside.
It's like you got 20 years is a long life.
It's a long time, yeah.
The
We're gonna have to do
materials.
a lot of,
Just the materials, not
Exactly.
the structure, but
yeah.
the plastics and the metals and
To
stuff.
be, orbiting and near the sun.
Right.
and
So
all
this
that.
this system, it's a little outside of our scope of work. It will be insulated to protect against radiation, if that's what you're hinting at.
Well, just in general, just
Yeah.
think of a piece of plastic
Right.
sitting in your backyard for 20 years
Yeah.
and what happens to it.
Yeah, it's been a challenge to find the material, just because we really need to take that into consideration, because the intent of the satellite, its main functionality is based off of the optic system. So it's going to be interesting to choose that.
Okay, I'll be interested when you come
Yeah.
back, what kind of materials you end up picking that are going to last 20 years.
For sure.
What's the environment in space? What's the temperature range that the satellite will actually see?
I would say it depends on where in the orbit, right?
So we do want to keep around a 450 kilometer orbit at all times.
Depending on the side of Earth, we don't have the exact number, but there are some drastic extremes that we're taking into account. We don't have an exact figure for you, sir.
So really what I'm asking is, when you design the cooling system, you should possibly also be a heating system, if need be, to stay in that 40 C range.
Right, so.
And then you also have to take into account the fact that whatever you put in has to survive 20 years. So when you're thinking about cooling, what I want to make sure when you come back to us, you show us that you can maintain that satellite at your prescribed temperature range over its prescribed light.
Just to mention something that I didn't go into detail earlier. So the way phase change materials work is when it changes phase, let's say it'll be on the hot side of the orbit, it'll change from a solid to a liquid. When it melts, it absorbs all that heat, and then when it gets to its cold side of its orbit, all that heat can go back into the components. So we have heaters on the components, we're trying to minimize the amount of power that those heaters actually input into the components and maximize the amount of heat that gets transferred back into the components.
So, you figure out all that.
Right, so as it switches
So
between.
you come back and tell us that, on one side of its cycle, you needed to use this much energy, and that side you didn't use any.
Yeah, we'll have all that data.
And you still have enough energy to go 20 years.
Mhm.
That, or you have a way of getting energy to the system to ensure 20, like the solar cells or whatever.
Just to interrupt 1 second, sorry sir, because I'm like mostly involved with, and his cooling system is for internal, so he actually is not exposed to the external environment temperatures. He just focus on this one, but it ranges from -60 to 200 degrees Celsius.
So is the system isolated substantially enough that the external environment's not going to have any influence on the internal environment?
So there is a next team, which part is that external, he's taking care of the external cooling system and he's taking care of internal. Because internal components, they are heating up all the time when they're using.
Sure.
So that heat is trapped within inside, and for the external components, you have, let's say, multi-layer insulations, or there are different insulation material that we put it in. Also the solar cells, it avoids your external heat going in, but at the same time, you have internal heat generation. So he's focusing on solving problem for internal components.
So currently our heat can't escape to the exterior, and none of the heat on the exterior can come into the interior.
Okay, so just make sure you set those boundary conditions
Right.
for your models, so we know your boundary conditions.
Are you gonna make some parts, so when you come back, we're gonna see some pieces?
Yes, we will
And
definitely.
you're gonna try to beat them up, shake them, bake
Yeah.
them,
That's
Hold them, everything.
yeah,
salt spray, humidity, all that good stuff,
yeah,
to see what lasts and what doesn't?
yes, definitely.
Okay,
It'll be interesting to see.
that'll be interesting.
Yeah.
How do you guys plan on testing this? I know you mentioned weather, but how do
So for the internal thermal cooling system specifically, we will be using the Emory Lab. They have a vacuum chamber. So we'll be putting all the components in there and actually testing the heat output of them to make sure our simulations actually match what is going to occur while it's in service for its full life. We're also going to take into account the fact that there will be only a certain amount of its total orbits that will be on and off. So we're going to have kind of like a cyclic operation. So we'll be using that. We'll be using the weather balloon testing to actually bring it up and see if our optic system's working and if our system's working, and if we're actually getting our sensors and getting the data and stuff like that. And I think you're going to use the.
Yeah, we have a plasma lab here where we'll be developing the micropulse plasma tester and testing that and its sensitivity and how much trust it's producing.
And also simulations.
Yeah.